Okay, so let us just continue with collisions. We had already discussed the collisions of two masses on a line. So we said that, okay, we calculate the initial momenta, the final momenta, and equate the two. Well, in general, the collisions will not be on a line. So if you are playing pool, for example, bilardo oynuyorsanız, the collisions, you don't want collisions in a linear collisions. You would like to hit a ball, hit one of the billiard balls by another ball, such that after the collision, one of the balls will move in one direction and the other ball will move in the other direction. So this is what you would like to have while you are playing the billiards. So this is the case. You have one ball hitting in this example, I will just be assuming that the other ball is at rest. Or you can say that if you have a system in which one of the balls is at rest, you can always go to another reference. Oh, okay, so if in your original problem, if both of the balls are moving, you can always go to a reference frame in which one of the balls are at rest. So by just making this assumption, we are not really losing any generality. This is quite a general. This will be quite a general result. Now, if you start with one ball, the second ball, after the collision, the two balls will be moving in different directions. So this is our question. This is our system. What can we say about this system, about the momentum conservation in this system? Well, the momentum, I repeat, the momentum conservation of a system is quite a general result. Of course, you have to be careful about what you are defining as your system. In the previous two questions that we discussed, we had the stone and the earth, and you jumping and the earth. You could have taken yourself in the last problem. When you are jumping, you could have define your system as yourself. In that case, the change in the momentum of you is determined by the external forces acting on you. But in that case, there is the gravitational attraction acting on you, which is not caused by one part of your body. So your momentum will not be conserved because there are external forces acting on your body. But when you consider yourself and the earth together, when you jump, of course there are forces acting on you, which is causing your velocity to change. But there are also forces acting on earth, which is causing the velocity of the earth to change. So the change in the momentum of the earth and you system will be given by the external forces. But if there are no external forces, then the momentum will be conserved. Now, if there are external forces, by the way, the rate of change of momentum is equal to the momentum change in a very small amount of time is the external force times dt. Now, when we talk about collisions, we usually assume that dt is very small. If you imagine this ball bouncing from the floor, you see that it is hitting the floor and then bouncing up. The collision is almost an instant. So the external forces in an instant, if they are finite, if they are small, that they will not cause any momentum change. So you can just imagine, let's say you can have two balls, you just throw them up such that they will collide in the air. Well, in such a system, there is an external force, so there will be the momentum of the system as a whole will not be conserved throughout the trajectory. But if you just consider what will happen just before the collision and right after the collision, well, this will be equal to the weight, which is some finite number. dt will be 0. So the momentum change during the collision, which takes a very small fraction of a second, will be 0. So that is what we will be assuming when we are discussing collisions. In collisions, even if there are external forces, the collisions take such a small time that the external forces will not change the momentum of the system. Yes? Well, you see, in this derivation, well, why only the external forces remain? Well, mainly because the internal forces, they cancel. Well, internal forces will cancel as long as they satisfy Newton's third law. Whether they are magnetic forces or gravitational forces or any other kind of force doesn't really make any difference. As long as they satisfy Newton's third law, the momentum will be conserved, independent of the type of force. Now let's come to this problem. So we have a mass, another mass. This is at rest. This is moving with some velocity v1. Let's say this has mass m1, this has mass m2. So the initial momentum of my system, the momentum vector of my system, is nothing but m1 times v1. Since the other one is at rest, it is 0. After the collision, this will have a velocity, let's say, va. The other one has a velocity vb. This is mass m1. This is mass m2. So the final momentum will be equal to m1 times va plus m2 times vb. Well, we know that momentum is conserved as a vector. So these two vectors have to be equal. m1 va, v1 should be equal to m1 va plus m2 vb. Now, since everything is happening in a plane, you can just choose your coordinates in the plane as x and y coordinates. If two vectors are equal, then their components along the x direction and along the y direction, they have to be equal. So we have these two equal. Okay. So this is the initial velocity. This is the final velocity. So these are the components of the momenta in each direction. So this is, if this is theta, this is phi. Va, the velocity of the A after the collision, is its magnitude times cosine theta in the x-hat plus Va times sine theta in the y-hat. Now Vb is equal to Va times cosine phi in the x-hat, now Vb, plus Vb times sine phi in the y-hat. So this Vb, okay, sorry, this has to be phi. Va has to be, no, these have to be theta, these have to be phi. Okay, so these are the sine phi, sine, cosine theta, sine theta. I will correct it. Okay, now you should be objecting me. I said that Va is Va, the velocity of A is Va cosine theta BA. Yes. Now, I said that the components of A is Va cosine phi in the x direction and Va sine phi in the y direction. Do you agree? Minus? Who said minus? Okay. Well, if phi is a positive angle, then I should have a minus sign over here. In this diagram, if phi is a positive angle, I agree with you that I should have a minus sign. But remember, I am defining the signs of my angles such that if they are above the x-axis, I define them as positive angles. If they are below the x-axis, I'm defining them as negative angles. So, for example, if phi is 45 degrees, the y component of VA should be minus sine 45 in the y direction. But since I'm defining phi to be minus 45 rather than 45, plus sine of minus 45 is minus sine of 45. So that is why I still have this plus sign over there. So because of this sign convention of the angles, I have everything plus in this expression. Convinced? Could I convince you so easily? Okay. So this, the initial vector, the momentum is only in the x direction. That is how I choose my x-axis. The final momentum has the x and the y-axis. Okay, this is the one is x, the other one is the cosines are in the x. This is in the y direction. So the component of the momenta in the x direction, which is given by this number after the collision and given by this number before the collision, they have to be equal. And the momenta along the y-axis, which is 0 initially and has this value after the collision, these two also have to be equal. Now, if you consider the unknowns, how many unknowns we have? If you remember our one-dimensional collision, we only had 2 unknowns there. So momentum conservation gave us one equation relating these unknowns, and we needed to have one more relation to solve for the final velocities. Now, here we have the unknowns are the final speeds and the angles that the final velocities make with the horizontal, or the final velocities make with the initial velocity. We have 4 unknowns. And to solve for these 4 unknowns, I need 4 equations. I have 2 of them. But I still need 2 more. Yes? Plus. This is plus. Yes, that is what the phi, okay, let's do an explicit example. This is x, this is y. So this is my VA vector. And let's just assume that this angle is 45 degrees. So this VA vector will be equal to the magnitude times cosine 45 in the x direction minus VA vector sine 45 in the y direction. Okay, you agree with this? I have a minus sign. But this thing I can also write as VA cosine of minus 45 degrees in the x direction plus VA of sine minus 45 degrees in the y direction. Because sine of minus 45 degrees is equal to the minus sine of 45 degrees. Now, in this case, I have this plus sign. They both are equal. Now, I just choose the convention that whenever an angle is below the x-axis, I will define that angle to be minus an angle. So this phi degrees over here, this phi that appears over here in this particular example is minus 45, not 45. So since it is this phi already contains that minus sign, I have a plus sign over here. So this is still a plus sign because the minus is here. Phi is minus 45. Well, again, I can just have the elastic collisions. But remember, elastic collisions, the conservation of kinetic energy is only a relation between the magnitudes of the velocity, is a relation between the speeds. So it gives me only one relation. It's not a vectorial relation. It is just one relation relating the unknown speeds. So here are my unknowns. I have 2 equations from momentum conservation. This is another one equation relating VA and VB to the initial velocities. I have 3 equations now. Well, if I have 4 unknowns, I cannot really solve it. So to make use of momentum conservation in such an elastic collision case, I need to measure at least one of these unknowns. I have to be given the value of theta, for example. Theta can take an arbitrary value. And here we see that any one of these we can just pick up theta. Theta can have an arbitrary value, but once you measure theta, all the other parameters will be determined by that value of theta. In the case of one-dimensional collision, saying that we have an elastic collision already fixed the final speeds. We don't have any freedom. What the system will make is already fixed. There will be no change, no surprises. But here, just requiring the energy conservation will not be enough to determine what the final outcome of the collision will be. I have to have some more information. Or I can say that theta is arbitrary and everything else will depend on the value of theta, or phi if you like. Now in the case of the completely inelastic collision, that is these two systems just collide, stick together and move as a whole, I have the equality of these two velocity vectors. Well, each vector has two components, so this is two equations. This already tells me that the speeds are equal and the angles are equal if they stick together. So I had already two equations. I have two more that gives me four equations for four unknowns, and I can determine what the outcome is. Now, this slide again, we had already discussed this slide, but I just would like to mention one more thing. Now, you see, if we write the kinetic energy of a two-mass system in terms of the center of mass and the relative motion, this is what we have. In the absence of external forces, we know that the total momentum of the system cannot change, no matter what happens inside the system, whether they collide, whether the collision is elastic, inelastic. The center of mass velocity cannot change, because the only thing that will affect the center of mass velocity are external forces, whose sources are outside my system. If there are no such forces, then the center of mass velocity is always constant. So this can never change. Now, when we say that the kinetic energy is lost, the only freedom we have is in this term. This is the internal energy. When we say the kinetic energy is lost, it is this internal energy, the kinetic energy due to the relative motion of the objects, which just disappears. It is converted to other forms of internal energy. So it is when, for example, when you have two objects sticking together, they will be deformed. Okay, so here comes the deformation energy if you wake him up. Okay, so when we have two objects that are deformable, they are no longer point objects. When they collide, like the Earth and the deformable jumping me, the center of mass velocity will be constant. The kinetic energy due to the relative motion will disappear, but it only means that it will be converted into some other form of energy in my system, like the deformation energy in my system. But the center of mass energy still will be constant. Now, this is the maximum possible energy that you can lose. This cannot change. This is the maximum amount of energy that you can lose. In the completely inelastic collision, what happens is this is completely lost. So the relative speed is zero. If the relative speed is zero, it just means that the final objects are moving with the same speed. So that is what we mean by completely inelastic collision. Now, in the case of a completely elastic collision, well, this thing should stay the same, because we are saying that in an elastic collision, the energy is constant, energy is conserved, kinetic energy is conserved. So this thing has to stay the same. In the one-dimensional case, the only way that v squared stays the same is that in the collision, the relative speed goes to minus the relative speed. That is the only freedom I have in the case of the one-dimensional motion. And we had already seen that energy conservation plus momentum conservation meant that the relative motion of the objects, it just changes sign. We had proven that v1 minus v2 is equal to minus v1 prime minus v2 prime. This is something that we had proven explicitly. But here we already see that in the one-dimensional case, if this quantity, well, this cannot change. If the total kinetic energy doesn't change, it means this cannot change. But we know that there is some change over there. The objects are moving, so the velocities are changing somehow. The only possible change is that the v goes to minus v, so that the square doesn't change. Now, in the case of the two-dimensional or three-dimensional motion, remember, it's a vector. The velocity is a vector. V squared should stay the same. The relative velocity vector should stay the same during the collision. if you only impose energy conservation. But if the magnitude of a vector is constant, you can still have the orientation changing. So the orientation is still free to change. So in a two-dimensional or three-dimensional collision between two objects, the relative velocity, its magnitude stays the same, but its orientation is still arbitrary. So in fact, that was the arbitrariness we had seen already, because just imposing energy conservation, we had 3 equations for 4 unknowns. There was one arbitrary parameter there, which we had to determine by some other means. And that, in fact, that arbitrary parameter is the orientation of this velocity vector, in which direction is the velocity vector pointing. It can, after the collision, it can point in arbitrary direction. The only restriction is that its magnitude has to be the same. Okay, so that is kind of all for today. Any questions before you leave? Then see you on Thursday.